All right, today we're going to introduce electric fields. Now, the people in Physics 252, we already introduced this. This is a pretty picture showing electric field lines between two charges. And so we're going to learn what these mean and why we use them. Because just because you can do them doesn't mean you have to do them. We want to understand why. First, a question that relates to what we've been talking about. A particle with a positive charge of plus q is the distance r from a particle with a negative charge of minus 2. So we have, oh, come on. There. Q minus 2q. And the Coulomb force that the positive charge exerts on the negative charge is written as plus F. So we have plus F. The plus is telling us the direction. So apparently in this problem, this direction is positive. And F is telling us the magnitude. And then the question is, what's the magnitude and direction of the Coulomb force that the negative charge exerts on the positive charge? So first, let's start with breaking it down. Is the force positive, 0, or negative?
Acting on the other way?
Yeah, the charge on the one that's not, or the force on the one that doesn't have a force shown.
Negative.
Okay? Why do you say negative?
Because it'd be going in the opposite directions. It has the opposite charge.
Not because it's opposite charge.
Or because they're attracted.
Because, well, we can answer it most easily by going just to Newton's third law. For every action, there's an equal and opposite reaction. So it has to be opposite. The other thing to do is to say these are going to be attracted, which I think is what you said. And so if it's pulling the negative one in the positive direction, then the positive one has to be in the negative direction so that they can be attractive toward each other. So we answered the easy question and said that it's going to be negative. So we've ruled out the top ones. And then what is the force going to be on that positive charge due to the negative? Is it going to be F or 2F in magnitude?
It's going to be equal to F.
It's going to be equal to F. And what's a good reason for that?
Charge doesn't matter.
Well, charge matters. But there's once again two answers. One is going to the third law, equal and opposite. The other one is just looking at the equation. There's our equation that gives us the force, and the force is just proportional to Q1 times Q2. It doesn't matter which one is bigger, which one's smaller. It's just the product that matters. So the force is going to have the same magnitude on either one because they're going to have the same product of charges. All right, now for the electric field. Electric fields are a way to simplify our lives. It does not feel like it's simplification, at least at first. But it simplifies our lives because it allows us to take a charge or a collection of charges and determine what the force on any other charge I bring near it is going to be. So the whole idea of the force field, and you're going to have to forgive me, the people who are in Physics 252, is something that we have explored a lot and never used the word for. We have already used a force field a lot, and that is that. The G vector, what have we called it always? Well, the G vector, so it's not F. Okay? Being a little more specific, the acceleration of gravity. That's what I've always called G, is the acceleration of gravity. But the acceleration of gravity is, by the definition of a force field, a force field. Because G was equal to the force of gravity vector divided by mass. The force of gravity is determined by the product of the masses between two objects. And so if I want to find the force of gravity on my body, I'm going to take G, my gravitational force field, and multiply it by the mass of my body, because mass is what the force depends on. So the definition of the force field is the force divided by the important parameter, what we like to call a charge, that the force depends on. So gravitational force, the charge for gravitational force is mass. That's what the force depends on. For electric field, the electric force depends on the electric charge. And so the electric field is defined in exactly the same fashion as E vector is the electric force divided by charge. So in practice, what you do is we'll start with a point charge. If I have a point charge, so that blue globe is not a point, is it? Oh, no, that's not a point. It has volume. But using a mathematical calculation that Newton did, it's called Newton's synthesis. If I have a spherical distribution of charge, it behaves exactly the same as if all the charge is at the center and is a point charge. So a spherical object with charge uniformly distributed can be treated as a point charge. And so I'm going to take that blue thing and call that my point charge. And my question is, what will the force be on some unknown charge out here due to this charge? Okay, I'm standing right in front of this for most people. What will the force be out here at point P due to the charge Q? And so we say, okay, the force is equal to K times the charge, capital Q, times lowercase q is the charge of what we call the test charge. The test charge is the one I'm saying, what will the force on this charge be? So point charge and test charge, I know is confusing terminology. The point charge in this case is the charge I'm finding that's causing the force, and the test charge is the random charge that I'm bringing to see how big the force is going to be. And then I divide it by r squared. So that's using Coulomb's law to find what the force is going to be. But then I say, what if I bring a different charge? What if I bring a charge that's 3 nanocoulombs instead of 1 nanocoulomb? How does it change? That's the whole idea, the question you're asking when you're dealing with electric fields. So what we do from this is we say, okay, let's say the electric field is equal to the force electric over the point charge, or the test charge, Q. And so that's going to be K, capital Q, lowercase q, over r squared, all divided by lowercase q. The lowercase q's here are going to cancel. And I have the electric field. Now I've been writing this as a vector, but I did not show direction. I should put an r hat here so I'm not a complete idiot. So there's the electric field due to that point charge. Or excuse me. Yes, due to the point charge. I said it right. Right. Point charge and test charge. Easy to make a mistake. So that's the electric field due to a point charge. Now, if I bring any charge and I know what its value is, I can simply say the force on this charge is going to be the electric field multiplied by this charge I brought in. Now, this equation, remember I started without writing the unit vector. I strongly recommend that if you're dealing with point charges and stuff, you do the magnitude separate from the direction. Just like I said when we're doing forces, do the magnitude separate from the direction. So the magnitude of the electric field is kq over r squared. What about the direction then? Well, from Coulomb's law, we know that opposites attract and likes repel. So if you have a negative point charge, as shown in the picture here, the negative point charge is going to attract positive charges. So if Q is positive, then the force is in the same direction as the electric field. So I know if I put a positive charge there, it's going to go into my globe, my capital Q. And so that's the rule for the direction. What direction would the force be on a positive charge? For positive charge, the force would be force would be into a negative point charge. So for a point charge, the electric field is always pointing into the point charge. On the other hand, if it was a positive point charge, what direction should the electric field point? Out, because a positive would be repelled away from it. So electric field always directly into a negative charge, direct charge. So that's how you get your direction. And then for point charge, KQ over R squared for the magnitude. Question?
So whenever I'm trying to think through the directions of the electric field,
Yeah.
I get kind of confused whenever I think about like the orbital theories or the cloud theories, where they're like electrons are moving like in a region. So is there a way that you can kind of combine these ideas where it's like they're moving out, but they're also like in an area, or are they just two separate models?
Well, I have a picture coming up with water molecules where I think the ideas play into what you're saying. So I'm going to hold off to there and ask you, Ken, if it doesn't do anything to clarify.
Okay.
Thank you.
What does the R hat mean again?
R hat means in the direction that's separating the two. So in this case, R hat is going to be pointing this direction. So, hey, look, there's the equation we've been working with. Yeah. Make sure we understand just the terms I've been using. A point charge has a net charge of minus 10 nanocoulombs. What direction do the electric field lines point? So here's my point charge. And just to make sure we're totally clear, up is coming out of the screen. Down is going into it.
2 west.
I made 2 west? No, that you just can't read my N. My N has an up down to make the first, or down up actually to make the first stroke, and I was sloppy on it. I was looking at the east thinking that's what you were talking about at first. So what's the answer? What direction are the electric field lines going to point here? Okay, I have 2 answers for E. Okay, that's all I'm going to draw because I've got stuff down below. That's correct. Electric field always points into a negative charge. Doesn't matter what's around it, it's always going to point into a negative charge. Michael?
So what we say is like negative 10 nanocoulombs. It's always negative on the negative charge. Like it's talking about a negative point charge.
Yeah. Right, so if it had been a positive, it would have been out. A problem, and actually this is one of your homework problems. Homework problem? I don't know. I couldn't have assigned this problem yet. I don't know. Maybe I did. I don't know. I'm pretty sure I saw this problem when I was assigning homework problems. I may or may not have assigned it. So let's do this problem. It's very similar to one of the problems that we had in class on Wednesday. A small sphere with a mass of 5.10 grams is hanging vertically from an insulating thread that is 12 centimeters long. By charging some nearby flat metal plates, the sphere is subjected to a horizontal electric field of magnitude 7.20 times 10 to the 5th newtons per coulomb. As a result, the sphere is displaced 6 centimeters horizontally in the direction of the electric field. So from that terminology, I can say the electric field is going this direction, right? Notice that it says subject to a horizontal electric field of this magnitude, so I put horizontal lines. What's the angle? I swear I changed this to a theta. I swear I did. That the thread makes with the vertical. So now we have a problem. How do we find the angle? Trigonometry, the end, right? We know the hypotenuse, we know the opposite side. So we can immediately say, what trigonometric function relates opposite and hypotenuse? Sine. So I'm going to have sine of theta is equal to 6.00 centimeters over 12.0 centimeters equals 1/2. Well, most of us know that gives us 30 degrees. So I have 30 degrees. That was straight trig. There was no physics in part A. Part B, what's the tension in the string? What would you do to find the tension? Okay, Nathan's method is perfect. Start with your free body diagram. Your free body diagram, what forces are acting on this? You have the force of gravity acting downward, the force due to the electric field to the right, and the force of tension like this. So just like we did in class, last class period, I'm going to put force of tension, force of gravity, force electric. Here's my theta. And so Nathan said, let's relate force of gravity with the force of tension. So that's adjacent and hypotenuse. What trigonometric function is adjacent and hypotenuse? Cosine. So I'd have cosine of theta is equal to force of gravity over the force of tension. Therefore, the force of tension is equal to the force of gravity over cosine theta. And so then I have to actually do some math. That's going to be equal to 5.10 times 10 to the minus 3 kilograms. Remember, units are important. Times 9.80 meters per second squared divided by cosine of 30 degrees.
Where did you get the kilograms from? Oh, just kidding.
So what does that give me?
First function I got 0.057.
0.057 what?
Actually, 7. Another 7.
771?
Yeah, 7. Sorry.
Okay, there's our force of tension. How many sig figs do I have? 3. How many digits did he give me? 4. Why? Because it allows me to not lose precision as I go through my calculation. Right? For my correct answer, it would be 0.0577 newtons. The one more makes so I'm not going to lose precision in my next step. Now the final one. What's the charge on the sphere? How do I do that? Okay, first I need to find the horizontal force. So I will find the horizontal force by using trig again. I'll use tangent because I know the adjacent side, 5.1 times 10 to the minus 3 times 9.8. Replaced force gravity with mg. Whoops. No, I did. And the force for electric charge with QE. And then my final step is going to be solve for Q. And this time I've run out of space. I'm not going to write mg tangent 30, but it's 5.1 times 10 to the minus 3 times 9.8 times tangent of 30 divided by 7.2 times 10 to the 5th. Notice the unit of the electric field here. It says Newton per Coulomb. Well, since we defined electric field as force per charge, that kind of makes sense, doesn't it? Force is units of newtons, charge is units of coulombs, so electric field should be units of newtons per coulomb. Listen.
So the electric field is different than the force electric.
Right. The electric field is used to calculate the force electric. The force electric is the electric field multiplied by the charge. And that is the point of using the electric field, to make it easy to calculate the force. Anyone? For some reason, I took my calculator into my office. I guess there's one up here. Okay, so it shows 0.0000, I don't know how many zeros, 4. I actually did that on a test my freshman year in college. I got the problem wrong because it was like, 3, 6, 2 something, and I just put the 4 because that's what the calculator showed. Still irks me today. Did anybody actually get an answer?
4.007.
This time I wouldn't have lost credit. So 4.01 times 10 to the minus 8. Yeah. 40.1 nanocoulombs. All right, that's the kind of problem we've been dealing with, right? Except for it's easier with the electric field if you know the electric field, because the calculation for the force due to the electric field is simpler than the force between 2-point charges. This here is the actual derivation that I prepared for something I did 3 slides ago. The electric field due to a point charge is magnitude is K times the charge of the point charge divided by the distance you are away from that point charge squared. So if you have a point charge, you can find the electric field from that. If you have 2-point charges, how are you going to find the total electric field due to 2-point charges? I'll ask the question in a different but equivalent way. If you had 2 charges and you want to find the force on the third charge due to those 2 charges, how did you find that force? As exemplified by this side of the classroom in class on Wednesday.
Trigonometry?
Trigonometry, let's back up. Before you did the trig, you had to
Find the vectors and add them together.
find the vector forces for each one and add them together. And that's what you do with electric field as well. Because the only difference is you're dividing by Q for the same exact work. So you take the vector of the electric field from one plus the vector of the electric field from the other, you add them up. So this gives us, see, that's the words right here. This gives us a new thing, but I guess I have time, I'm going to get there. But before I work this out, I want to point out a few things about electric field lines. We draw electric field lines, we call them lines of force, because they show us what the force will be if I put a particle there. So the electric field lines point the direction that the electric field points. If I have a positive charge, what direction should the electric field point? Outward. So electric field lines should point outward from a positive charge. Negative charge, they point in. If the charge is in isolation, then you're just going to have straight lines that go off to infinity. Electric field lines always start or stop at a charge or at infinity. So that's a first simple rule. Now a second rule that's not quite as obvious What's happened to the strength of the electric field when you get farther away from a point charge? It weakens. It drops off as 1 over distance squared. What happens to the lines that are radiating out as you move away from the charge?
They spread out from each other.
They spread out from each other. Hence, we can draw the correlation from those two statements that Dimitri answered. The spacing between the lines tells you how strong the electric field is. If the lines are close, it's a strong electric field. If they're farther apart, it's a weaker electric field. And of course, the charge that you start with tells you about how strong the electric field is as well. And so if you have higher charge, it's going to have more lines coming in or out. So as a rule of thumb, if you're drawing electric field lines, decide, okay, I have 4 and 3. I'm just going to have one line coming out for each nanocoulomb. If I have 12 and 15, I might make it for every 3 nanocoulombs, I'm going to have one line coming out. But be consistent within a problem, because the electric field strength is going to have to do with the spacing of those lines. And so if I have a bigger charge, I should have more lines coming out proportional to the ratio of the charges. Those words are going to come up on a slide coming up, so I will review it again. Just wanted to get it out there now so I don't forget in case I take all my time doing problems. So here's another problem. 2 point charges are located on the x-axis. So here's the x-axis shown. The first one, plus 0.6 microcoulombs, is located at 0. The second one, minus a half microcoulomb, is located at 0.40 meters. And then I want to find what's the electric field out there. So we've already spoken the words of how we do this, but let's reiterate. How am I going to find the electric field at point P due to these 2 point charges?
Vectors.
Add them as vectors. I find the electric field due to each point charge and then add them as vectors. So I'm going to have the magnitude of electric field 1 is equal to K Q1 over R1 squared. Electric field for 2 is going to be K Q2 over R2 squared. I do need to pay attention to direction. So what direction is the electric field due to charge Q1 at point P? Answer should be either, well, there could be wrong answers too. I won't just give you the options that are right and diametrically opposed to correct. What direction should the electric field be at point P due to charge Q1? Is Q1 positive or negative? And electric fields go which direction from positive? Out. So what direction is out from Q1 at point P? To the right. So that's the direction of E1 there. So I'm going to change this into a vector by putting in the positive x direction. What about Q2? What direction will its electric field at point P be? It'll be in, which is to the left. So I'm going to make that into a vector as well. So then my total electric field at point P is equal to K Q1 over R1 squared minus K Q2 over R2 squared in the plus x direction. If the thing in parentheses is negative, then it's going to be in the minus x direction, right? So now I just have to put the numbers into the calculation. So I, of course, just don't give myself enough space. There's the first one. Oh, let's make our lives easier. I'm going to factor out the K. Notice I just put the magnitude of the charge. I didn't put the minus sign because I've already taken account of directions elsewhere.
Should you convert to Coulombs?
In my calculation, yes. So the 0.6 microcoulombs is going to be in my calculator 6 times 10 to the minus 7 coulombs. Really important. So what do we get for this?
Negative 7,019.
Negative 7,019. Yeah, that seems right. Minus 7 and 10 to the 9 gives us something in that ballpark. Is that what other people got? With no counter voices, I'm going to assume that's correct. Now, I'm going to add on to this problem where's the electric field equal to 0? How would you go about that? I think that's right. Yeah. So how would I find where the electric field is 0? I'm looking for a method, not for actual calculation. Go ahead, Chad.
You take Coulomb's law, set force equals to 0, and then plug in K of the charge and solve for R.
That would also work, but I'm going to make it with electric field since I asked about electric field, right? That would give me the place, but I'm just going to say for electric field. So, and by the way, I'm going to restrict it to on the x-axis. So we don't have to worry about any difficult two-dimensional aspects. So we're just going to say the electric field, just as we just did, is K times Q1 over R1 squared minus Q2 over R2 squared. Set that equal to 0, which gives me Q1 over R1 squared equals Q2 over R2 squared. Something I really should explicitly do is put these absolute value signs so that we don't make silly errors. And then I need to separate R2 is equal to R1 minus 0.40 meters, not separate, but substitute. So I have Q1 over R1 squared is equal to Q2 R1 minus 0.40 meters squared. Now it becomes not that hard of a problem. Cross multiply and square root. You have R1 minus 0.40 meters times the square root of Q1. Keep in mind its absolute value just is equal to R1 square root of Q2. So I would have R1 times square root of Q1 minus square root of Q2 equals 0.40 meters square root of Q1. Right? Whoops, can't do that. And so that gives us what the radius is going to be where you have 0 for the electric field.
Which electric field? Just,
The electric field on the x-axis.
I mean, which charge?
Due to both of them.
Both of them.
Combine both. So that's another standard problem that's given to make sure you understand how to add electric fields. Mira.
Go back and just-
And I really should have been more careful. When you do square roots, you get a plus or minus.
How will we figure out which?
That gives us two answers now. Huh?
How will we figure out which answer is irrational on a plus or minus for a distance like that?
Well, it really should have absolute values on these Q's, so they're all rational. Right, because this isn't a square root of A minus B, it's square root of A minus square root of B.
Well, I mean,
Or
if
plus
we do
root.
plus or minus, we're going to get different answers.
Right, because there are 2
But-
points, there are 2 answers.
Oh, so there's more than one.
That's why I'm saying I should have been more careful. I should have put the plus or minus here. Put the plus or minus here, because that plus or minus then, I got sloppy. There's no plus or minus there. I got sloppy because I skipped it the first time and tried to throw it in quickly. I moved this over, so that's why it became a minus plus. Not that it's going to matter to us which one's which.
Well, does that mean there's going to be 2 answers? Then?
Yeah, there's 2 answers. There's one if you put the minus sign in the denominator, and there's one with the plus sign in the denominator.
Okay.
I have a question. How come we have to, like, if you go back to the other part, how come we have to subtract the Q1 from the Q2 when it's divided, right there?
This right here,
Yeah, why did you have?
that was because of this right here.
Oh, so you just, okay.
Right, I used my picture to assign the directions there. And then I put it so the electric field has directions, but it got the directions by me looking at the picture. And so, once again, I'm sloppy on not putting those absolute values, but when I did my work, I did it with the absolute value of the charge, and the sign was based on my external work. All right. We're not going to do this problem. 3-point charges are placed at the corners of a rectangle as shown in the figure. What's the electric field due to these 3 charges at the 4th corner point P? We'll talk about it and move on. So what is the method to find the electric field at point P?
Find the vectors,
Find the vectors from
the other 3 charges.
each of the other 3 charges and add them together. So I can look and I can say, aha, away from the charge, so I'm going to have That will be my electric field due to charge 3 toward, whoops, that's reversed. Yes, I realized when I read through the second one. Toward a negative, away from a positive. And so I'm going to have to calculate what each one of those magnitudes are, break them into components, and add the components. And you had a whole semester of experience with the components. So I'm not doing them as a matter of course simply because it does take time. Here's what has the words about drawing the fields. And so I talked about 2 rules. The strength of the electric field is proportional to this, inversely proportional to the spacing. The closer the electric field lines, the stronger the electric field. And the electric fields always start or end on a charge or infinity. But there's some other things here. Because we calculate a net electric field, you can never have electric field lines cross each other. Because if they cross each other at the point where they crossed, what direction would your vector be? You can't have 2 directions, and if they cross, you have 2 directions where they cross. So electric field lines can never cross. And the force, of course, is always going to be parallel to the electric field at the point. So you can see in this lower picture, is the electric field stronger at point P or at point R? Stronger at P because they're closer together. Yeah, just vectors. There's pictures of a positive and negative charge in their electric fields if they were in isolation. If they're together, we have to add them as vectors. In this case, it's kind of easy. If I add them as vectors, well, this line is clearly, they're in the same direction, so it's going to go like that. If I take like this point here, I have one going like this and one going like this. So it's going to add up. What direction would I get from those? Assuming equal charges, one's plus Q, one's minus Q. So they have the same magnitude there. What's that going to add up to? Horizontal. So I'm going to have like this. And so the lines are going to do something like that. And, what about this one? Something in that ballpark. So if they're opposite charges, then your lines are coming together, separating, coming back together. This is the situation that's attractive. And so this is where DJ was asking about, thinking about the electric orbitals and the bonds and stuff. When you have bonds and you have an attraction between the molecules, the electrons are shared, and you see bonds that look something like this when you look at the electron densities. It's not the same thing looking at the electron density and looking at the electric field lines. But the two look similar. If they're coming together, then it's going to be attractive. Here's an example where there are different charges. So this one has -2 microcoulombs. This one has +3. So let's count the number of lines going in and out. So the -2, they're coming into a negative. And we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 coming in. So that means we have 4 lines for every microcoulomb in that picture. Now, if we look at the other one, if we're consistent, we had 4 for every microcoulomb here. How many lines should there be here? 3 microcoulombs, 4 lines per microcoulomb. 12. And so if we count those, 1, 2, 3, 4, 5. Yep, there's 5 above and below. Total of 12 lines there, so that the ratio of lines is proportional. The ratio of lines coming out of each charge is proportional to the charge. When we study Gauss's law, that's all Gauss really observed. Gauss said, wow, if there's more charge, I have more electric field coming out. And that's the basis of Gauss's law that we'll learn about. I already talked about this. They cannot cross. Move past that. A dipole. In this class, I usually don't talk about dipoles very much. What does dipole mean? Has two poles. That's all it means. So if it's an electric dipole, it has two electric poles, a positive pole and a negative pole. And so if I have electric dipole, well, let's think about it. I took my stuff away here. Let's pretend this is our globe. This globe has a really big, what charge is it on top, right? Was it positive or negative? Positive. So a really big positive charge. Now we bring around something that has an electric dipole moment. That means that it has a separation between the positive side and the negative side. If this is positive and it's like, let's start with this orientation. What's going to happen between the positive charge and this positive charge? They'll repel. What about the negative in this positive charge? Track. So there's going to be a torque that makes it rotate like this. But now here's the trick part. The negative charge is closer. The positive charge is farther. The Coulombic force is an inverse square law, so the closer one, if these are the same charge but separated in space, the closer one's going to be the stronger force. So what direction will the net force be on my dipole now? It's attracted, it's going to be pulled in. And so electric dipoles are naturally going to be attracted to a charged object, because no matter what charge this is, it's just going to have a torque to rotate it so the side is attracted is closer, and then in she comes. So if I have that charged globe, and there's an electric dipole in the air, you know what's an electric dipole in the air? Water. If there's water in the air, those water molecules are going to be rotated and then attracted. And then when those water molecules touch or get close enough for arcing to occur, touch the globe, then what happens? If the globe is positive, my dipole comes up and touches, and what's going to happen? An electron is going to transfer from my dipole onto the positive globe, making the dipole now have a net positive charge. Well, what direction is the force between positive and positive? Repulsive. So now my ionized water molecule flies away. What did that do? It depleted the charge on the Van de Graaff generator. So the Van de Graaff generator runs oh so much better in dry conditions than in wet conditions. In winter, the temperature of the air is cold. If it's cold, the air can hold far less moisture. So even, my wife looks at the humidity. Stinking Nebraska, it's 80% humidity. Yeah, but it's 26 degrees. That means there's virtually no water in the air. It's holding, 80% of what it can hold. 80% of virtually nothing is nothing. So the air is really dry in the wintertime here because of the cold temperatures. Hence, things like playing with the Van de Graaff generator work a lot better. If you do it in the summer, it's humid. It's hot temperatures and humid, which means a lot of moisture in the air. And we're talking like 1,000 times more moisture. Hence, the charge of that Van de Graaff generator will dissipate very rapidly, just going through the air. Other cool demos, things that I definitely won't do. I can take the Van de Graaff generator and pour water next to it. What's going to happen to the water as it comes close to the Van de Graaff generator? It'll be attracted in. And so the water will actually curve toward it as you pour it close to it. Why am I not going to do this? Because if I get too close, it'll pull it in, it'll hit the electric motor, and then bad things happen. That's why I don't do that one. I suppose I could hold the Van de Graaff generator sideways to do it safely. I thought about that till now. Especially since it's far, it's bad. Messed up. That's a cool thing. Balloons. If you take a balloon and you rub it on your hair, what's happening? Okay? Static electricity. What is the static electricity at its fundamental point? Fur, that's what my hair is, and rubber is rubbing electrons off of my hair and onto the rubber. And so the rubber is going to have a negative charge, the balloon's going to have a negative charge, my hair will have a positive charge. Then I take that balloon and I can stick it to the wall. Why can I stick it to the wall? It would actually only work if the wall has electric dipoles that it can't conduct from. So electric dipoles in the wall will orient so they attract it, and if it can't conduct, then it just sticks.
Is that why it works with some walls but not with others?
Yeah. Here's the pictures that I specifically was talking about. This page shows water's hydrogen bonding and shows the electric fields, and here then it shows the bonds. Okay, we're out of time. Have a happy Sabbath. And we're now, what, 7.5% done with the semester or something like that?
I have two questions.